Hey folks, wanted to throw together a quick summary video about graphing motion. That's an issue that people struggle with sometimes all the way through a class, but graphs in general are such a useful tool. We're going to use them more as we continue our lab work. So if we're not really solid on how to interpret graphs, we need to get there. We're going to go back to the position, velocity, and acceleration versus time graphs and look at, in particular, translating between those. So we have this idea that when we read a graph, we might be looking at, say, the vertical value, the y value, and how it changes over time. We might be looking at the slope of the graph and what it means and how it changes over time. And we might be looking at the area underneath that graph, or between the x-axis, the horizontal axis, and the curve. And so each of those has a different meaning on each one of these different graphs. Now, first off, the y values here, it's going to mean position. The y value is the position value. The vertical axis is the position axis. Here the velocity, and here the acceleration. Those ones are pretty straightforward. They're on the axes. Now, slope is a little bit more challenging. Here, if I did the slope, it'd be the rise over the run of some graph up here. The rise being a measure of how the position changes, divided by the run, which is how the time changes. Rise over run, or position change over time change, on this graph is going to give us velocity. So if I wanted to look at the slope here, that would mean velocity. Down here, the slope, the rise over the run, would be the change in velocity divided by the change in time. Change in velocity over change in time is the definition for acceleration. So here the slope is equal to acceleration. Okay, now last up, I'm losing my marker here. Last up on this, we've got acceleration. If we did the rise over the run, the slope on that one, the change in acceleration over change in time, turns out is not a quantity we're going to deal with in this class. The name for it is jerk, how acceleration changes over time, but like I said, we don't have to deal with it here. So slope I'll go ahead and put down jerk, but not useful here. Just not something we do in AP Physics 1. All right, now the other thing we might look at here would be area under the curve. So if I just imagine a graph here, just do a horizontal line, this area underneath would be some number of seconds, some amount of time, times this position and how it changes. So maybe some number of meters times some number of seconds. There's no quantity that would have units of meters times seconds. So it turns out that that also is not a meaningful quantity. The area under the curve there is not anything useful. Now in this one, if we did area under the curve, we'd have some number of, say, meters per second. So I'll draw the rest of this rectangle here. We'd have some number of meters per second on this axis, some number of seconds on this one, meters per second times seconds. That would give us a number of meters. Now if we just look at the velocity multiplied by the time, say we're going 5 meters per second over a time of 20 seconds, for a time of 20 seconds, we would find out that we do 5 meters per second times 20 seconds, which would give us 100 meters. That's going to be a displacement. It's how our position changes over this time period. So the area is equal to the change in position, or displacement. All right, and then last one, acceleration. If I have some graph here, it doesn't matter what shape these are, by the way. I'm just picking an easy shapes, rectangles to work with. The area of that rectangle would be some number of meters per second squared times some number of seconds. My units on that are going to be meters per second. Or I could think if I'm accelerating at a rate of, 2 meters per second squared, and I'm doing that for a time of, say, 10 seconds, finding the area on this would be 2 meters per second squared times 10 seconds. We'd get 20 meters per second, which it turns out is going to be the change in velocity during this time period. So every second our velocity changes by 2 meters per second, and we go for 10 seconds, we get 20 meters per second change. So the area here is equal to the change in velocity. Now, that's all well and good, but one of the things we're going to be asked to do periodically is convert from one graph to another. Now, using these ideas of slope and area under the curve, we can do that. It just sometimes takes a few different steps, and it's a tricky process conceptually. I'm going to start out with a velocity graph, and that way we can practice going both directions. You see, when we do the slope of this one, I get to this graph, and I do the slope of this one, I get to this graph. So slope here is velocity, slope here is acceleration, velocity to acceleration. And I can go the other direction by looking at area under the curve. So the area under here is going to be change in velocity. The area under here is going to be change in position or displacement. So in calculus, we talk about moving this direction as being taking derivatives, time derivatives of these functions, and going the other direction would be taking integrals of these things. If you're not in calculus, you haven't had that before, that's fine. Area and slope work just fine for what we'll do. So let's start out with a velocity graph here, and then we'll just practice making a conversion to a different graph type. So let's start with this graph, and I'm just going to make some marks to indicate sort of where these significant moments happen on each one of these graphs. And I'll go ahead and mark the 0 here, pass through 0 velocity. All right, and then here's a change in the shape of that velocity graph. Okay, and another change in the shape of that velocity graph. And then the end of our motion. Okay, so starting with the velocity graph. Let's go this direction first. I think people generally find that to be a little bit easier. So we're going to look at the velocity graph and try and learn about acceleration. So over here, I'm looking at which one of these things tells me about acceleration, and I've got slope is going to tell me about acceleration. So first off, we've got a horizontal line, which means slope is 0. So the slope here is the acceleration. That means during that same time period, we're going to have an acceleration of 0. Get this. Acceleration of 0. There we go. And I lost my axis. Let's fill that back in. There we go. All right, now we go from a slope of 0 during this section to now a slope all the way through here that's going to be a constant value because it's a straight line. Straight lines have constant slopes. And that's going to be a negative slope. It's pointing downward. So a constant negative slope for this one. So from here all the way to here, we've got a constant negative slope. And we have kind of a jump there. Now, that's not something that can really happen. Can't have an instantaneous jump in acceleration, but we simplify these a little bit and pretend that acceleration changes only in these very discrete time moments, really, not intervals. Next up, we get to this section, and again, we've got a slope of 0 for that. We have a horizontal line. So back up to our axis. Okay, and a jump there. All right, and last section, we've got some positive slope for that, and it's another straight line. So we've got some constant positive slope. So something like this. And a jump there. All right, next up, let's go the other direction. And this one, I think, has a little bit trickier conceptual understanding required, because now we're going to say that on this graph, the slope represents the velocity, which is what we were told here. So everything we read about velocity here has to become the slope up here. So, for example, here I've got a constant positive velocity. That means up here I need to have a constant positive slope. Now, first off, where are we going to start this graph? We don't really have any information about that. All we know is how fast this object is going. not where it is. If I say I'm driving 20 miles per hour, you don't know where I am. So the same thing happens here. Let's just go ahead and start it at 0. And then we have a constant positive velocity here. So a velocity that doesn't increase and it doesn't decrease. And it's above the 0. So we got positive, constant positive velocity. So up here, velocity shows up as the slope. That means a constant positive slope up there. So that'll be a straight line with a positive slope. Next up, from here to here, this little section, we start out with a positive slope like we had up here, but we're going to be decreasing in that slope. So, we start with a positive velocity, and so we decrease it to 0 velocity. Up here, where velocity shows up as the slope, we need to start with a positive slope and decrease to a 0 slope. Positive velocity to 0 velocity, positive slope to 0 slope, so that means we're going to have a curve. And we're going to just level out up here. So just a very slight curve so we get to a horizontal section there. Now we have 0 velocity becoming a negative velocity, and so up here we're going to have 0 slope becoming a negative slope. So again, a curve downward this time. So we go from 0 slope to negative slope. That gets us down here. Now we have a constant negative velocity. So we need to have a constant negative slope here. So another straight line. All right, and last thing that happens here, we have our negative velocity becoming a little bit less negative. So we're going to have this negative slope become a little bit less negative as well. So this is another curve. And this time, something like that. Getting a little bit less steep over time. They're not quite to 0 velocity, so not quite to 0 slope. We don't quite get to horizontal on this one. Now we can check our work just by thinking through the slope of this one more time. Here we had constant positive slope. Slope means velocity, so that should show constant positive velocity down here. And, yep, constant positive velocity. Our slope then decreases. It's still positive for a little while here, but it's getting less and less steep, and we eventually get to a high point on that graph with 0 slope. So we go from positive velocity to 0 velocity, positive slope to 0 slope. Next up, we go from 0 slope, or horizontal right here, to a negative slope. We're pointing downward. We go from 0 velocity to a negative velocity now. Here we have a constant negative slope. So down here, a constant negative velocity. And last up, we have a curve again. So we have a negative slope, but it becomes a little bit less negative, closer to 0. This one we have a negative velocity, but it becomes a little bit less negative and closer to 0. As I mentioned, that one takes a little bit more conceptual practice just to get a handle on, but all things that we need to be able to work with. Now, as far as numerical values, you can certainly calculate the slope or the area under the curve for each different section on these things to get numerical values if you were given, of course, numbers on your graphs. So that's kind of a separate piece. This is more just about getting the general shapes for these graphs correct. Thanks very much for watching. Please let me know if you have additional questions on these. You can do that in the comments or in person for those of you who I get to see on a regular basis. If you've learned something from this, by all means like and share this video with people you think would benefit from it as well. Thanks very much.